We're now going to look at the process of extraction and purification of an organic product, including fractional distillation, Raoult's law, and the properties on which extractions are based. We're going to see fractional distillation and then we'll see Raoult's law. So when we look at compounds that are volatile compounds usually have high vapor pressure. Now, what is vapor pressure? If we look at the previous page, vapor pressure is the pressure when a vapor is in equilibrium with a liquid or a solution. So if a substance is volatile, it will have high vapor pressure because there's going to be a large amount of gas particles, right? And when you have volatile compounds, they evaporate faster. Now, when we do fractional distillation in the column, let's say you have a mixture, both of the components or all the components in the mixture are eventually going to produce vapors. So vapors of different components will evaporate, but they will condense again and again at different heights. So if you remember the fractionating column, you have blades or you have beads, and depending on the height of the column, you're going to have condensation taking place. Each cycle of condensation and evaporation will enrich the mixture with more volatile components. Now, the more volatile it is, means the lower boiling point. So we normally say that the one with the lower boiling point is collected first. So why is it collected first? Because the gas is going to get more concentrated is going to become enriched with the vapor of the more volatile component, increasing its mole fraction. Mole fraction is how many moles of component A do you have in comparison to number of moles of component A and B together. Right? So it increases the mole fraction and increases the purity as we go up the column. Vapors of the more volatile component will move up the column, while the less volatile will stay as liquids and fall back in the flask. So let's say A is the one with the lower boiling point. This is going to be collected first. This will move up the column, will get concentrated, while even if B moves up, it will condense back into the flask. Eventually, the more volatile component will reach the top, pass through the condenser, and reach the receiving flask. And this is going to occur as a continuous process, which allows mixtures to be continuously collected and purified. Once we get the different samples, we can carry out mass spectroscopy, gas chromatography, or HPLC to further analyze what component we purified. Now, the Raoult's law, it explains that as we're moving up the column, both substances will be present in a certain proportion according to their vapor pressures. Therefore, you might need to do a series of distillation to completely purify the sample. So let's see Raoult's law. So Raoult's law applies to ideal solution and considers that an ideal solution is a mixture where the two liquids, or whatever number of liquids you have, the liquids behave in the same way as if they were pure. For example, octane and hexane would behave the same way as octane would behave on its own and hexane would behave on its own. And the vapor pressure of an ideal solution would be the sum of individual vapor pressures of the components. So this is the Raoult's law for one component where PA is the vapor pressure of A over the mixture. P star A is the vapor pressure over pure sample, and XA is the mole fraction. Let's see all of this in a question. So you have acetone. The vapor pressure of acetone is given, and the vapor pressure of chloroform is given. 200 grams of each is mixed. What is the vapor pressure of the resulting ideal mixture? So, resulting ideal mixture, according to the Raoult's law, would be the vapor pressure of acetone plus the vapor pressure of chloroform. Now, we need to calculate each one with respect to the mole fraction, right? So, PA is the vapor pressure of A over the mixture. This is obtained by multiplying the vapor pressure of pure A times the mole fraction of A. So, vapor pressure of pure acetone is given. We need to find the mole fraction of acetone. Now, to find mole fraction of acetone, we need number of moles of acetone divided by the total number of moles of all substances in it. So, we have the mol of acetone which is given. We have the mass of each one. So, from this, we can find the number of moles of acetone. I'm going to write acetone as A and chloroform as C. So number of moles of acetone would be mass divided by mol. And number of moles of chloroform would be mass divided by mol. Now from this, we can get the total number of moles, which is a sum of these two values. Now from the number of moles of each, we can get the mole fraction of A. So the mole fraction would be the number of moles of acetone divided by the total number of moles. And similarly, the mole fraction of chloroform would be the number of moles of chloroform divided by the total number of moles. So you can calculate this or you can leave it as it is. And the vapor pressure of A would be the vapor pressure of pure A, which is 201 times the mole fraction of A, which is this. So you can calculate this. And the vapor pressure of B in the mixture will be the vapor pressure of pure B times the mole fraction of B. And therefore, the vapor pressure of the resulting ideal mixture will be A plus B, PA plus PB. So this is what the Raoult's law says, is that the vapor pressure of an ideal solution is the sum of individual vapor pressures of the component. So we just add the two and you get the sum here. And with this, we end with topic D.9.